Picture 2 tons of steel, leather, and glass sitting at a red light. Nothing about it screams race car. There's a trunk full of groceries in the back, and a booster seat clipped into the rear bench. Then the light turns green, and in less time than it takes you to read the sentence, that ordinary family sedan is already past 60 miles an hour. Not eased into it, slammed into it, hard enough to press the air out of your lungs. A speed that a generation ago belonged to fighter jets being flung off aircraft carriers now belongs to a car you could buy at a suburban dealership. And the part that should really stop you is this. The thing making it happen isn't some hand-built, 6-figure exotic power plant. It's a motor small enough to lift with 2 hands, built on an assembly line, wound out of copper and magnets, and, strangely enough, aerospace-grade carbon fiber. Inside that unremarkable metal drum, something close to violence is happening every time you press the accelerator, and understanding why nobody else in the auto industry has matched it tells you almost everything about how Tesla actually pulled ahead. Start with the part of the motor that does the work, the rotor, the spinning core that turns electrical energy into the motion of the wheels. In Tesla's most powerful motors, that rotor doesn't just spin fast. It spins at roughly 20,000 revolutions per minute, a number that belongs on an industrial turbine, not underneath the back seat of a family car. At that speed, physics stops being polite. Every gram of copper and steel inside the spinning rotor is being flung outward by centrifugal force, and that force doesn't grow gently as speed increases. It grows exponentially. Double the rotational speed, and the outward force doesn't double. It roughly quadruples. Push an ordinary rotor into that territory, and it doesn't just wear out faster, it can warp, crack, or, in the worst case, come apart entirely. For decades, that reality forced every electric motor engineer on the planet into the same uncomfortable trade-off. You could build a motor for raw power and accept that it would run hotter, wear faster, and need heavier reinforcement to survive its own output. Or you could build a motor for efficiency, tuned for smooth, gentle, long-range cruising, and give up the explosive punch that makes an electric powertrain feel alive. Power on one side, efficiency on the other, and a wall in between that nobody had found a cheap, scalable way to knock down. It wasn't treated as an unsolved puzzle. It was treated as settled physics, the electric motor equivalent of gravity. You picked a side of that trade-off, and every major automaker built entire engineering departments around living with it. Tesla's answer to that wall shows up in the Model S Plaid, the version of the car built to prove a point as much as sell to customers. Elon Musk described the motor's development directly. The innovation isn't a heavier casing or an exotic alloy. It's a machine that wins carbon fiber filament around the copper rotor under extremely high tension, wrapping it so tightly that the fiber squeezes the rotor inward, holding it in compression. That compression is the whole trick. Musk explained that the carbon sleeve has to clamp the copper rotor tightly enough that it won't loosen even as temperatures swing and the metal expands and contracts at a different rate than the carbon around it. Get that tension wrong, and the sleeve either fails to do its job or cracks the material it's supposed to protect. Get it right, and you have something that behaves less like a car part and more like the wrapped composite shell of a rocket motor casing. A comparison that isn't accidental, since carbon fiber filament winding is a technique borrowed directly from aerospace and high-performance racing, where engineers have spent decades using it to build things that are strong, light, and able to survive forces that would shatter solid metal. The machine that does this winding wasn't bought off a shelf. Tesla built it in-house through Tesla Automation, the German engineering group the company acquired and expanded specifically for this kind of precision manufacturing work. That matters because winding carbon fiber around a metal rotor at automotive production volumes, with the kind of tension and heat control needed to make every single unit survive 20,000 revolutions per minute without failing, is not something you can simply outsource. The tolerances are unforgiving. Wind the fiber slightly too loose, and the sleeve won't hold the rotor together at speed. Wind it slightly too tight or cure it at the wrong temperature, and you risk damaging the very part you're trying to protect. A mistake doesn't produce a weaker motor, it produces scrap. That difficulty is a large part of why other manufacturers haven't simply copied the idea. Carbon-sleeved rotors themselves aren't unheard of in specialized high-performance motors. What's rare is doing it reliably, at scale, cheaply enough to put in a mainstream production vehicle. Here's where the story stops being just about a bigger horsepower number and becomes about something more interesting. What that carbon sleeve actually buys you isn't only speed, it's stability. An unreinforced rotor spinning at extreme RPM tends to flex and vibrate almost imperceptibly, and that tiny imbalance bleeds energy away as heat, noise, and wasted motion. A rotor clamped tight by a carbon fiber sleeve stays truer at speed. It resists the tiny deformations that waste energy. And a motor that spins true with less wasted vibration and heat is a motor that's also more efficient, not just more powerful. That's the part that quietly breaks the old rule. Tesla wasn't just choosing power over efficiency. The carbon wrap let them push both at once, because the same fix that let the rotors survive higher RPM was the fix that also kept it from wasting energy while doing it. Engineers who examined the technology, including independent analysts who modeled the Plaid's performance curve, noted something unusual. The motor's power output stays remarkably flat almost all the way to its red line, instead of tapering off the way conventional motors do as RPM climbs. That flat curve is exactly what you'd expect if the rotor isn't fighting itself at high speed anymore. The results are hard to argue with. The Model S Plaid uses 3 of these motors, 1 up front, 2 in the back for independent torque control on each rear wheel, producing something in the neighborhood of 1,000 horsepower combined, enough to push the car from a standstill to 60 miles an hour in under 2 seconds. That's a figure that puts a 5-seat family sedan with a proper trunk and a full set of driver assistance features in the same conversation as hypercars built in tiny numbers by hand, for many times the price. And unlike a hypercar, the Plaid still has to be a car people actually live with, one that can sit in traffic, cruise the highway for hours, and be driven by someone who's never taken a performance driving course in their life. That combination, brutal acceleration, and everyday usability, is exactly the pairing that the old rule said you couldn't have. None of this happened by accident, and it didn't happen because Tesla decided one day to chase a bragging rights number. It happened because the humble little motor bolted under the back seat was quietly one of the hardest problems in the entire electric vehicle industry, and solving it well pays off in ways that go far beyond acceleration times. A motor that runs cooler doesn't need as much cooling hardware wrapped around it. Fewer pumps, fewer radiators, fewer coolant lines, less weight, less cost, and fewer parts that can eventually fail. A motor that's smaller and lighter for the power it produces frees up space and weight budget elsewhere in the car. And a motor built around a manufacturing process Tesla developed and controls itself, rather than one bought as an off-the-shelf component from an outside supplier, gives the company a cost advantage that's very difficult for a competitor to copy quickly. Because copying it means rebuilding an entire specialized production line, not just buying a part. That's the deeper reason this story matters. For years, the assumption in the auto industry, and honestly, the assumption plenty of Tesla skeptics held too, was that legacy manufacturers would eventually out-engineer the upstart. Ford, General Motors, Toyota, Volkswagen. These are companies with a century of accumulated manufacturing knowledge, supplier networks built over generations, and the kind of industrial scale that lets them design and tool a specialized part almost on demand. On paper, that advantage should have crushed a smaller, newer company that was still working through production bottlenecks and missed deadlines of its own. And for a while, it looked like the gap really was closing. Legacy automakers rolled out electric vehicles that were, by most accounts, genuinely competitive, well-built, comfortable, backed by dealer networks and brand trust that Tesla didn't have. The narrative in the press started to shift from, "Can anyone catch Tesla?" to "The window is closing." But the carbon-wrapped motor is a reminder of where the real competitive edge in this industry sometimes hides. It isn't always in the flashy stuff, the giant touchscreen, the self-driving demo, the dramatic stage reveal with a truck that looks like it drove out of a science fiction film. Sometimes it's buried in the single most unglamorous, overlooked component in the entire machine, the part almost no buyer ever thinks about or could even name. Tesla poured serious engineering effort into a problem that most of the industry had quietly decided wasn't worth fighting: the fundamental trade-off between power and efficiency in an electric motor. and came out the other side with a solution that let it have more of both at once, in a package that's smaller, lighter, and cheaper to build than what came before. That doesn't mean the advantage is permanent, and it's worth being honest about the limits of what one clever motor design can do. Rivals are not standing still. Every major automaker has poured billions into their own electric drivetrain research, and carbon fiber sleeved rotors, once demonstrated to work at scale, are the kind of innovation that tends to eventually get replicated, even if it takes years and painful trial and error to do it well. Manufacturing a part with these kinds of unforgiving tolerances at high volume is genuinely difficult, and that difficulty buys Tesla time, not a permanent monopoly on the idea. There's also a fair question about how much of this performance envelope the average driver will ever actually use. Most Tesla owners will never take their car anywhere near 20,000 revolutions per minute or a sub-2-second launch. The vast majority of the benefit they experience day to day is the quieter kind, a motor that runs efficiently, wastes less energy as heat, and helps stretch the range of the battery pack a little further on an ordinary commute. Still, there's something genuinely remarkable about watching an entire industry's settled assumption get quietly dismantled by a spinning cylinder of copper and magnets wrapped in aerospace fiber. The rule that power and efficiency couldn't coexist in the same electric motor wasn't a minor technical footnote. It shaped how every EV on the road was designed, how heavy its cooling system needed to be, how far it could travel on a charge, and how hard it could accelerate without cooking itself. Tesla's carbon-sleeved rotor didn't just produce a headline-grabbing 0 to 60 time. It chipped away at the cost, weight, and complexity of the entire drive unit, and it did it with a manufacturing process the company built and controls itself, which is exactly the kind of advantage that's hard to shortcut. So the next time you see a Tesla launch from a stoplight hard enough to pin you into your seat, remember that the drama isn't really coming from a giant, exotic power plant. It's coming from a motor small enough to carry in your arms, spinning faster than most industrial machinery, held together by threads of carbon fiber wound tighter than almost anyone thought was possible to do at scale. It's a reminder that in engineering, the biggest breakthroughs don't always announce themselves with a dramatic reveal on a stage. Sometimes they're spinning quietly, 20,000 times a minute, in the one part of the car nobody ever thinks to ask about.